Hi, everybody. I'm Karthik from the University of Alberta, talking about Plasmon-Enhanced SERS detection of small molecules. The work I'm presenting was mainly done by this graduate student, Najia Mahdi, who couldn't be here, and that's why I'm presenting. Um, this is a session focused on nanotubes and nanowires. And titanium dioxide nanotubes and nanowires have the advantage of their high refractive index, their semiconducting property, their earth abundance, and so on, which is why they're used not just in sensing, but also as photocatalysts and photovoltaics and so on. And the vertically oriented structures give you particular advantages wherever you have charge separation involved, which could be in photodetectors, but also certain kinds of chemical and optical sensors. So there are two kinds of structures that my group really specializes on for use in sensing. The top is these nanotubular structures, which are formed by electrochemical anodization, similar to the process used to make porous alumina, which is found on the back of your iPhones. And the other structure gives us these vertically oriented nanowires. It's formed by solvothermal synthesis, which our previous speaker referred to because that's also used for zinc oxide. Okay, so now coming to the topic of plasmon-enhanced SERS sensing, well, it's very well known in the SERS field that the electromagnetic enhancement factor that you get from a localized surface plasmon resonance is the fourth power of the for Raman spectrum, which means by introducing a plasmon resonance, in theory, you can achieve a 10,000 times higher signal. So that's the principle, and that is why a lot of groups around the world have been trying to make plasmonic nanocomposites. And the other reason being titanium dioxide is a particularly robust sensor on which naturally a lot of small molecules tend to adsorb and form self-assembled monolayers. So the combination is expected to be very powerful for yes, but that's the theory. The real problem, though, is that a lot of some recent work, 2014 and so on, has demonstrated that these 10 power 4 enhancement factors are actually extremely hard to achieve. Because when the calculations show that when you make the peak too small, you go off resonance and so on. So the real enhancement factors are actually quite low. But so this structure that I'm showing you is the structure which is basically these titanium dioxide nanotubes decorated by gold nanoparticles, a structure which a lot of groups around the world have been doing, including us in the past, because that's a very convenient way to make these kinds of plasmonic nanocomposites, which give you great ensemble performance compared to say hotspots generated by electron beam lithography without the cost. But when you actually look at the literature and look at the actual, when you do the calculations, and we did this for a whole bunch of papers and looked at what the actual enhancement factors are, and there's a very simple way you can calculate that because the electromagnetic enhancement factor is directly proportional to the Q of the resonance, which is the resonance frequency divided by the full width at half maximum. And as you can see, the Qs are very small, whereas the work we did, which I'm going to show you in a little bit, we achieved much higher Q factors, almost a factor of 2, and in some cases maybe even 3 compared to other work. So what did we do that's different from what I showed you? So this is what a lot of the other groups are trying to do: grow nanotubes, decorate them on the outside by gold nanoparticles. What we tried to do is to embed the gold nanoparticles inside the nanotubes. Now, why would we want to do this? Well, there's a paper from the Van Dyne group from a while back, from about 10 years ago, which showed how sensitive even the SERS action is to the permittivity of the surrounding medium. And so you have this direct sentence from the paper which showed that the highest sensitivity was obtained when the gold nanoparticles were fully embedded inside a titanium dioxide film. And there's ways to do that using co-sputtering and atomic layer deposition. But that's again has its limitation. If you completely embed gold nanoparticles in film, well, you don't get a high surface area that you need for your molecules to actually adsorb. So what this does is tries to get the best of both worlds. So the gold nanoparticles are partially, or in some cases, fully embedded in the walls of the nanotubes, while the high surface area of the nanotube structure still allows the molecules to adsorb. So that was the concept here. And what I'm showing here is I'm showing some of the ensemble plasmon resonances of similar systems. You can see there's quite a few that are broad, nanoscale, and nano letters, ACS materials and interfaces. And when we use this partial embedding, we immediately saw Q factors and extinction coefficients that were much larger. And the way we did it is we made a multi-layer stack by sputtering. It was we sputtered titanium and then co-sputtered titanium and gold. So we created this alternating layer stack, and then we subjected it to electrochemical anodization, and that resulted in this plasmonic nanocomposite where the nanoparticles were embedded inside the nanotube. So these are, transmission electron micrographs showing the nanoparticles in the structure. And one interesting materials-based feature that we saw, so these are scanning electron micrographs again, and this is the TEM, again, gold nanoparticles on the in the cross section, and the top view still shows this nanotubular morphology. Now, one interesting materials aspect, something that we observed was we observed heteroepitaxial interfaces between the gold and the TiO2, which means we had the lattice plane aligning along certain specific directions. Now, why is that significant? Because for the plasmon resonance to be really effective in SERS, there's the electromagnetic component, which is not the whole story. There's also a chemical component that's known as interface chemical damping, also or Landau damping. And that in the gold nanoparticles is very important, is related to factors such as the yield of hot electron injection. Okay? So when you have a heteroepitaxial interface, that dramatically enhances the possibility of direct injection of hot electrons from the gold to TiO2, which then can um, uh, really improve your signals. And we also did some testing of the nonlinear properties, which also showed that indeed the plasmon resonance was causing this expected effect. This was a two-photon fluorescence, and the reason we use this as a good probe is because this phenomenon also has a 10 power 4 dependence, similar to Raman scattering. So coming to the Raman scattering here, so this is the equation which people use to claim the fourth power enhancement, but that comes with a lot of caveats, as I mentioned. So when you use higher concentrations of rhodamine 6G, you see all the different peaks in the R6G spectrum. So you see the 394, the 520, the 613, 774, all of them. Now, as you start decreasing the concentration, as you're looking for smaller and smaller quantities of rhodamine 6G, the peaks diminish. So you have, so the intensity decreases, but also the type of peaks that you observe decreases. So this is with 10 power minus 5 molar of rhodamine 6G, and now you're still seeing a lot of different peaks, so you get a unique fingerprinting of rhodamine 6G. Okay, but then when you go to even lower concentration, so up to 10 power minus 6 also we see many peaks. But now when we are trying to push the limits at 10 power minus 7 and 10 power minus 8, which is the lowest we went, so we do see a couple of peaks which are still characteristic of rhodamine 6G, which are the 1088 peak and the 940 peak, but as the intensity or as the concentration changes, the intensity of these different peaks doesn't scale linearly and doesn't scale in the same fashion. So the ones that seem to be most robust are the 1088 and 940, and this may have to do with the particular way very dilute solutions of rhodamine 6G adsorb onto the surface of TiO2. Okay, but this is a very promising result because in these ensembles, we are achieving similar performance for SERS to what some reports traditionally have only achieved with techniques such as electron beam lithography, which is very expensive and is not scalable. So that is the promising aspect. And 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 so while the search results I showed you are really new, the method we use to actually build these kinds of nanocomposites we published earlier this year in 2017 in ACS Applied Materials and Interface. So to conclude, heteroepitaxial interfaces and very strong LSPR are observed in anodically formed AuTiO2 nanocomposites. There's a strong enhancement of both the Raman scattering and the two-photon fluorescence, and the great advantage is because it's TiO2, you can just take off the molecule by an oxygen plasma, and then you can reuse it, and it's reproducible. So that's a huge advantage. Thank you.